So the next question of CC-START114 is yet another matrix problem. So yeah, in this question, we'll be given a n value, and the constraints of n value are from 1 till 1000, and the number of test cases are up till 100, and the sum of n value across all the test cases does not exceed 10 power 6. All right. So for a given n value, we need to build a matrix of size n by n such that all the sub-square matrices starting from 1, 1 have the sum of their boundary elements equal to an odd number. Okay. Now let's see how let's construct a matrix for n equals to 3. Okay. So for n equals to 3, let's construct a matrix. Okay. So now we'll have let's take the sample cases only. 5, 4, 8, 6, 3. Okay. So the boundary elements for the first sub-square matrix is this one boundary element, which is basically 9. For the second one, it will be these 4 elements. So 9 plus 1 plus 4 plus 5. Okay. And for the one that ends with 3, 3, it will be 9 plus 1 plus 7 plus 8 plus 2 plus 3 plus 6 plus 5. Okay. So this equals to 19, this equals to 9, this equals to 19, and this equals to 41. And all these 3 values are odd numbers, right? Which means it satisfies the constraints. So this is one valid way of arranging the elements. And for a given n value, we need to find one such valid arrangement. So there could be multiple answers. So yeah, also all the values in the matrix should be in the range 1 to n square. All right. And all of them must be distinct. So basically placing all the elements from 1 to n square in this matrix, right? So yeah, let's see how we can solve this question.
So basically in this question, let us observe one thing. That is, my claim is, firstly, let's see why this is true. For now, let's say, let's consider this n by 2 floor part. Okay. If that is divisible by 2, that is if it's even, then let's construct it in one way. And if n by 2 is odd, if n by 2 is not 0, then we have one other construction. So let's see how we can do that. So firstly, let's consider n by 2 as even, case where n by 2 is even. So to dry run this, firstly, let's consider n as 5. So for n as 5, let us first draw a grid. These are the 5. So now we don't actually require the values of even and odd. So we know that sum of odd number of odds will be odd, and sum of even number of odds will be even. And sum of evens doesn't matter. How many events we have, or how many many events we have, that doesn't matter. Exactly. Only number of odds matter. So now, firstly, let's see how many odds we can have in n square. For n square, we can have ceil part of n square by 2 number of odds, right? Rest all should be evens.
Right.
N minus odds will be evens. So now let's try filling this with odds. Firstly, let's leave the diagonal blank and let us fill all this with odds. Now all this with evens. Right. So now, because lower triangle and upper triangle will have exactly same cells, we can say till now number of odds are equal to evens.
Right.
So now on this diagram, if we see there are n elements. So in this n elements, half of them should be odds and half should be evens.
Right.
If it's a odd, if it's of odd length, then half plus one should be by half plus one. We can say seal part of half should be odds.
Exactly.
And
right.
floor part of half should be even.
Right. Yeah.
So in case if I put all odds here firstly,
okay.
So we can see that number of odds are 2 more than number of evens. We can observe that. So now, okay, not 2, they are 4 more than the evens, right? Number of odds.
Right. Yeah.
So now, but in this configuration, we can see it satisfies the given criteria. That is, this will be one of the square matrix whose sum is odd. Then if we observe this square matrix sum is odd, this square matrix sum is odd,
right.
This square matrix sum is odd. Similarly, this square matrix also sum is odd.
Right.
Now,
so basically elements are like here there are 3 odds.
Yeah, 3
and
odds.
Then next there are
5 odds.
5 odds exactly. And
Next
then there
are
are 7
odds.
odds and 9 odds.
9 odds.
So it keeps going like that. Odd number of odds every single time.
Odd number of odds every single time. Yeah. So now we can observe one thing. Now we know 2 of the odds should be changed to evens.
Right.
Because there are 4 odds more than evens. So 2 of them should become evens. Then evens and odds will become equal.
Exactly. Yeah.
Equal or odds will be 1 more than evens. Because when n is odd, n square will be an odd number. So
right.
seal part of n by 2 odd should be present. So now from this we can observe if we count the number of odds, we can say it is n plus. Okay, we can just look at in this fashion. Instead, lower triangle is exactly same as upper triangle. So this part is this part is exactly same as this upper triangle.
Right.
So now only thing is the diagonal. So in this diagonal, 3 of them should be odds and other 2 should be evens. But because we are putting 2 more odds, we can say odds are 4 more than evens.
Right.
So this way we can analyze how many odds are more than evens. So now we need to change 2 of the odds to evens.
Right.
Now we know that if we observe this part, let us not change this whole part. We know that all the sub-square grids in this part satisfies the condition.
Right.
Now only thing is the lower, now initially if this is the odds configuration, then the lower part is also satisfying the condition, right? This part.
Right, yeah.
But now we need to make changes. So because we need to add 2 events here, similarly for any n by 2, for any floor part of n by 2 which is even, we need to add even number of events.
Events, exactly.
Because we need to add even number of events. Adding even number of events means we are removing even number of odds. Exactly. So if we remove even number of odds, that doesn't affect the period.
That doesn't affect the period.
So for that, we can just change the last 2 odds to evens.
So basically, the number of odds in the last 5 by 5 matrix were initially 9. But we removed 2 of them, so it became 7, which is still an odd number.
Which is still odd.
Therefore, it would still satisfy the configuration.
Still satisfy.
And we are just changing the last row, so everything before it is unaffected.
Yeah, unaffected.
Right. Yeah.
So similarly, because n is 5 here, floor part of n by 2 is 2. So 2 events, 2 odds should be changed to events. That means.
Yeah.
Exactly. Similarly, if for any n in the last row, we know last row size will be n. So from n, we need to change floor part of n by 2 number of odds to evens.
Exactly.
But this will only work if n by 2 floor part of n by 2 is even. That is because in this case we'll be removing even number of odds. So that won't, removing even number of odds won't affect the parity.
Right. Okay. So this works only in the case if n by 2, the floor part of n by 2 is an even number, right?
Floor part of n by 2 is even.
So okay, let's just see a test case and try the same logic for something that has a floor part of n by 2 as odd.
As odd, yeah. So
let's take n equals to 6, for example.
Yeah, let's take n is equal to 6. So this is n is equal to 6. Right?
Yeah.
So now let me index them. So now let us, as usual, put odds in this part, just like how we did the previous one.
Right.
So now we know if we arrange it this way, always every square matrix will satisfy the condition.
Yeah.
That is because whenever we are putting, one thing is common. So this part will have some parity, and for sure this part will have one lesser than the current value.
Exactly.
So both the parities will always be open.
I mean the same pattern: 1, 3, 5,
Yeah, 1,
7,
3, 5,
9, like that.
7, 9, and so on.
Yeah.
So now here, but here the issue is we need to place odd number of events.
And evens will go on that basis, right?
Events will go over here. For now, let's fill these with events. And we know now we know that there are 2 into floor part of n by 2 number of odds.
Right. Yeah.
More than evens. So that means we should replace 3 odds with evens.
Exactly.
So the way we can so just like previous one, if we replace, if we put evens here, till here it satisfies the conditions.
Right.
But it won't satisfy for the larger matrix.
Right.
That is because previously, because we were inserting even number of events and removing even number of odds,
right,
parity didn't change. But here we removed odd number of odds. Previously, parity of this matrix was odd. Now it changed to even.
Now it changed to even. Okay.
So that is why this couldn't be done with. This couldn't be done if floor part of n by 2 is even number.
That's right.
Sorry, odd number.
Okay.
If it's odd number. So in that scenario, let's see how we can make changes. So there can be many ways to construct, but one of the way to construct it would be we know that we need to add n by 2. We need to add floor part of n by 2 number of events and
right,
remove floor by 2 and floor by 2 number of number of odds.
Right. Yeah.
So that means let us firstly try removing these odds.
Like in this case, we need to add 3 events and remove 3
odds.
Right.
Because n by floor part of n by 2 is 3.
Yeah, exactly.
So let's add events over here.
Okay.
Now we can observe that this part is unaffected.
The part above, right?
The part above.
Yeah.
This part. This is unaffected.
Right.
Previously, the parities of all the submatrices, square submatrices were odd. Now also they remain odd.
Now also they remain odd. Right.
But this part, if we look over, once we put events here, this part previously it was odd, right?
Yeah.
Now it became even.
Exactly.
Similarly, this part it was odd, now it became even. And this part it was odd, now it became even.
So basically, the parity of the last 3 submatrices has changed.
Yeah, the parity of last 3 submatrices changed. So because the parity of last three submatrices changed, now what we can do is, our aim is to change the parities of all this, and these things parity shouldn't be changed.
Right.
Such a way we should try placing some odds, or if possible only one odd.
Right. Okay.
And the claim here is we can do that with one single odd.
Okay.
So what we can do is to change the parities. We can remove this odd and pull it to this point, and this becomes even. So if I pull this odd to this above part, we can see that this matrix will however satisfy, because previously it was down. Now we just pulled it to the upper.
Basically switching two elements in the boundary part, so that will not affect that.
That will not affect the answer. But now by pulling this odd up, previously when the odd was over here, that didn't contribute to this part.
Right.
This part, similarly this part.
Exactly.
And so on. This part in the last part also.
Right.
So now by pulling it to the top, this will contribute to all the lower things also, but it won't contribute to the upper square matrices. All those which are above it, they won't intersect with this.
Exactly.
But all those which are below it, they'll actually
this odd will
contribute to their boundaries.
Right.
So we can now we just saw that by placing evens here, we flipped all this to evens.
Right.
Even parity. Now by placing an odd here, this odd will flip the parity of all this
back to odd.
Back to odd, and this was odd because we just changed 0, which was contributing previously. Basically, this odd was contributing previously for this matrix, and now also it's contributing. So this cell's parity didn't change, but all these cells' parity changed.
Exactly.
So ultimately, we can observe that this matrix follows the given conditions.
Right. Yeah. I think this is clear.
So this way we can arrange. This way we can do the case two, depending on what.
And once we have where we are placing evens and where we are placing odds, we can just place them in any order.
Yeah, we can just place them in any.
Like we can just go sequentially. If we get odd, place one number, increment. Okay.
So for any n by 2 which is an odd, just replace the last n by 2 odds in the first column with evens, and wherever we have odd, like we know the n by 2 minus 1 cell.
Right.
For this n by 2 is 3. Float part of n by 2. Float part of n by 2 plus 1 would give us the above cell. So for the above cell, we'll just pull the corner odd to the top.
Exactly.
So this will be the corner odd. We are just pulling it to the top and changing this to E.
Right.
So if we just do this for any n by 2 which is a odd number, for any n by 2 which is an odd number, it will work.
Right. Yeah. Well, what will be the time complexity for this?
So here time complexity would be n square, as we need to fill the matrix. So we should travel over each and every cell of the matrix to fill it.
Right.
So it would be n square.
Okay. Yeah, I think that's clear.